All right, thanks, Murat. So this paper I'm going to present today is called State Machine Replication for Planet Scale Systems. Am I loud and clear? I just want to make sure.
Yes, and clear. We can hear.
Okay, all right. So this paper was presented at Eurosis a couple of months ago. What this paper is proposing is a replication, a state machine replication system for inter-region replication. So it wants to achieve fault tolerance, but at the same time minimize client perceived latency. That's their important goal. This is not the first paper to do it. There are other works like starting from Mencius and Epaxos a few like that came out many years ago. But the way this paper differentiates is in how it does these things. The first thing it tries to do is it keeps quorum sizes small by using fewer nodes than other protocols that are out there already. But similar to other protocols, it also goes leaderless. That is, any replica in the system can serve client requests. There is no special role, which brings us to no leader downtime as a big advantage, which is good for fault tolerance and availability. And it also provides better load balancing. Similar to other protocols out there like Epaxos, it also tries to give a one round trip commit for client requests in the best case. It is not possible always though. So when we compare Epaxos and with Atlas and also other protocols, basically I found that Atlas is a combination of existing techniques in a novel way. First, if you look at Epaxos and what it provides, the quorum size of Epaxos is 3n/4, and it goes leaderless, and it can provide one round trip decision that is, it's called fastpath, whenever there are no conflicts. Flexible Paxos was proposed recently, and the main idea there is to have a smaller normal case quorums by trading off with a larger recovery quorums. And Flexible Paxos was a leaderless protocol, and it was able to provide one round trip from the leader, while other nodes in the system would redirect the commands to the leader. Atlas provides a quorum which is smaller than Epaxos quorums, and the way it puts it is n/2 plus f. It basically differentiates between the number of nodes in the system versus f. Usually, before Flexible Paxos, we were always doing f. There was some relation between f and n, and Flexible Paxos kind of broke that down. And Atlas kind of sticks with that. It breaks the relationship between the number of actual nodes in the system versus the fault tolerance that you try to provide. And that quorum size for the fastpath is n/2 plus f. It is again leaderless like Epaxos, and whenever there are no conflict, it is able to provide single round trip decision all the time. But when there are conflicts, sometimes, or as they argue, like depending on what the F is, many times they can provide single round trip decisions. So let's look at how they build their quorums, because I found that was the most interesting part. To do that, let me start with Epaxos itself and see first how Epaxos got its quorums, and then we'll kind of go to Atlas and see how it builds its quorums. from FastPaxos, which was the first paper by Lamport to propose that nodes can propose commands directly rather than going to the leader and have like a fast path. So in that paper, there was this condition that said any two fast quorum and must intersect with a slow quorum, and that intersection must be non-empty, basically. The intersection of any two fast quorum and a slow quorum must not be empty. I think that was a statement from the paper. So when applying that to ePaxos, basically it found two quorums in this figure FQ1 comprising of nodes 1, 2, 4, 5, and 6. Each circle is a node, let's assume that. And if you have another fast quorum that cover nodes 2, 3, 5, 6, and 7, the intersection yields us nodes 2, 5, and 6. So now when we bring in a slow quorum, which is just a classical majority of 4 nodes, we can see that that intersection would yield us nodes 5 and 6. So what this gave ePaxos is that whatever decision was taken in any of the fast quorum could be retrieved in a slow quorum. Slow quorum was essentially used for recovery and also the slow path. So whatever decision was taken by a fast quorum was able to be retrieved in any slow quorum because of this intersection property.
Balaji, can I ask a question?
Yep.
In ePaxos, they want this to be more than the empty set, right? They want to be, they want this to be also the majority. The intersection would be the majority in the slow quorum, I think, right? Because otherwise you could make fast quorums majority, slow quorum majority, intersection would not be empty set, I think. But the fast quorum is chosen to be n/2 plus, basically.
It was f plus 1 by 2 plus f, I think. What you're referring to is the optimization that that they said that yielded to a complex recovery phase, right? So initially, when they started proposing that basic ePaxos, they kept their quorum to be 3n by 4.
Yes.
And then because of that larger quorums, their recovery was simpler. And yes, your point is correct in that because of that larger quorums, what you had in your recovery was the intersection of the slow quorum would somewhat get you majority from the fast quorum, actually. I don't think it was from the intersection it would get, but if you intersect with a fast quorum and a slow quorum, that fast quorum would get a majority. I think that is what you get. Yeah, I think so.
Yep.
All right.
I have just a question in this example.
Yep.
You have FQ1 and FQ2, which actually makes sense, but SQ could also be 1, 2, 3, 7. In that case, recovery will not be exactly the same. 4, 5, 6, 7 is just one SQ. There could be another SQ, right? And there could be multiple such SQs. It depends on which replicas were failing at that point of time.
Exactly. But in this case, if you talk about 1, 2, 3, and 7, 2 is still in the quorum.
Yes, but then there are 3 people who are, and then there are 3 people who are not exactly. You can create a scenario where the node. So in this specific example where you actually created, 5 and 6 were the 2 people who actually had the same set of transactions.
2, 5, and 6. 2, 5,
yes.
and 6.
And in your SQ, there is only 5 and 6.
No, so what you have to do is you need to first intersect the 2 fast quorums first, and then intersect with the slow quorum. So whatever you get from the intersection of those 2 fast quorums, you then take that and intersect with the slow quorum. So when you just intersect the 2 fast quorums, you get 2, 5, and 6, which is Yeah. So which is you basically get 2, 5, and 6, and then you take that and intersect with the slow quorum. Now you get 5 and 6. So that was basically what they argued for. Do I make sense?
Yes, yes.
Okay. All right, if I keep moving on, okay, let's look at how flexible Paxos achieves quorums. Basically, flexible Paxos differentiates between the number of failures versus number of nodes in the system. So that lets them, and also it says that phase one, if you look at like the two phases of the Paxos, what flexible Paxos said was you don't need a majority, you don't need an intersecting majority in a single, in the same phase for different proposals, but all you need is that the two phases, the recovery phase and the normal phase, must intersect. So they exploited this notion and they were able to get like a very small P2 quorum, I'm sorry for the typo here, and then a larger phase one quorum. Or vice versa. So usually people would opt in for the normal case P2 quorum to be small and then the P1 quorum to be larger. And this one right here in the figure with the orange, it could be the smaller phase two quorum where you usually run your normal case protocol, and whenever there is a recovery, you could intersect, you can have that large enough that it will cause an intersection with any normal case quorum, basically. And Atlas kind of merges these two concepts and builds its quorums. And the way it does is like this: it retains the slow quorum to be the same thing, like depending on what F is. So if F is 2, it says your slow quorum is F plus 1, which is 3 replicas. And let's say we have 2 such quorums. And from this, they start building their fast quorums. The first intuition they have, basically, I think, is that the quorums for the fast quorums must intersect. Otherwise, you cannot share any dependencies. So the smallest way you can have quorums intersect here is having a majority. So they cannot have anything less than a majority. So when you draw 2 such quorums in this example, you can see that those 2 quorums intersect at the replica 2. But the problem here is that you don't satisfy condition 1 of fast Paxos, which says that the intersection of any 2 fast quorums must intersect with the slow quorum. In this case, what can happen is the slow quorum cannot retrieve any dependency that 2 might have had. So this is basically a plain majority, and this doesn't literally work. And instead, what works is this n by 2 plus f. Rather than having n by 2 plus 1, they add f more replicas to their quorum, similar to what flexible Paxos did. Basically, it adds f more replicas for f fault tolerance over one node, which knows about the proposal already. So by doing that, they get this quorum, which looks like this, shaded in blue and then green. And the intersection basically yields us nodes 2, 5, and 6, which will have the same decision because they are on the intersection. And if you superimpose a slow quorum, which is in the orange shaded area, any slow quorum can now basically retrieve the result that the intersection of those 2 fast quorums did. Also, you can get in the phase 1 quorum from flexible Paxos and keep it as it is because it is already large enough that it spans both the fast quorums and the slow quorum intersections, and it can retrieve any dependency during recovery. So I think this is how they basically build the quorums, because this I found this to be much more intuitive to build by combining the fast Paxos property and also the flexible Paxos property.
Yeah, this is very nice explanation. Mm-hmm.
Okay, thank you. So this is what they get. So from what they, the result of what they get out of this is 3 properties. So they get smaller quorums, and they also get some relaxed fast path conditions. Unlike ePaxos, where you need all the replicas to agree with your dependency, Atlas is able to do fast paths with relaxed dependency conditions, which I'll give an example in the next slide. Also, what it gives is a simpler recovery protocol. What I felt like was what they mean by simplicity in recovery was it was much more equivalent to the base ePaxos recovery than the optimized versions of ePaxos. So in that sense, it was simpler than the complex ePaxos with the smaller quorums, fast quorums that they built. So let me give an example that they gave on their slides to explain how the normal case Atlas works. We have 5 nodes. The horizontal lines represent time, and the node 1 is proposing command A and node 5 is proposing command B. Initially, node A proposes A with an empty dependency set because it has not observed any previous commands. Same with node 5 for B. So it collects this view of the command and then it broadcasts it to all the other nodes. When the other nodes get it, 2 receives A first and then B. 3 receives A first and then B. However, 4 differently receives B first and then A. What this gives is basically when these nodes reply back to the coordinator, which is node 1, they receive different dependency sets. For 2, they receive empty dependency set from 2 and 3. And from node 4, they receive B as their dependency. Similarly, for B at node 5, what it receives is from 4, it receives an empty dependency set. But because of the receipt order in those nodes, B gets A as dependency from node 2 and 3. And this is basically the gist of it. So at 1, 2, and 3, the order of the command is basically A and then B. But at 4 and 5, the order of receipt is basically B and then A. Also, if you notice, the dependency B was only received from 1 process, while the dependency A was received from 2 processes at 5. And this is what basically decides if a fast path or a slow path is taken. So how many processes observed the dependency decides whether to take a fast path for a command. And it is as follows. Because F, let's assume that F is 2 in this case. Out of 5 replicas, you want F to be 2. And if each of the dependencies the nodes report are reported by at least F nodes, then you can take a fast path. In that sense, for command B, you can take a fast path because the dependency for B was reported by at least 2 replicas, and our F is 2. So immediately, replica 5 can just issue a commit message for command B. On the other hand, replica 1, it needs to take a slow path. Because B was only reported by one process, however, our fault tolerance F is 2, so we need to see B at least 2 nodes if we want to take the fast path, which is not possible in this case. So instead, they take a slow path and basically use the normal case flexible Paxos protocol to simply exchange the final dependency in this case, which is basically the union of all the dependencies, which is one element, which is B here. The paper also talks about different fast path examples. One of them being on the right. Let me come from the right because we can talk about ePaxos in this case and compare with Atlas. So if you look at figure D here, basically we have 5 nodes, and one is a coordinator. 2, 1, 4 send a dependency of A back to the coordinator 1. 3 and 5 are left out of the quorum, basically. In this case, in ePaxos, basically, because each one of the replicas all observe the same dependency set, which is A, they can take a fast path because the replies all match in ePaxos. In Atlas, it's also again possible if F is 1 or even 2 or even 3 in this case. They just give F equals 1 as an example, but it's also possible with F equals 2 and 3 because 3 replicas observe the same dependencies. Now let's move on to figure C. Here, because the dependencies reported are not equal, ePaxos cannot take a fast path. However, Atlas can because it only expects dependency to be proposed or shared by one node. In this case, even though A is shared by 3 nodes, the dependency B and C are only shared by 1 node each, which is node 2 and node 4. Atlas says even in this case, they can take a fast path because their F is just 1. That's not possible with ePaxos because their F is higher and their quorum, and they need matching replies. There is, in figure B, there is a case where both Atlas and ePaxos should take a slow path. And basically, when you don't get F for Atlas, the reason is basically 4 is the only node that returns B as the dependency, while no other node returns any other dependency, and F is 2 for Atlas. And similarly for ePaxos, because no node returns the same set of dependencies, it has to take a slow path.
Balaji, can I ask a question about the slow path? You explained the fast path in this figure, but if we go to the previous figure, my question is about the slow path that node 1 does, right? Node 1 does the slow path. It's not observing any new nodes. It's observing what it already observed. Actually, it's observing less than what it already observed. So what is intuitively, what is the new information we get from the slow path that makes us to be able to decide that, well, actually A does not have a dependency on B, B has a dependency on A, and we commit this, right? So 5 decides that I have a dependency on A. So after A, I will do my execution. My dependency is on A. And 1 did this, it found one guy reporting B. Since F is equal to 2, it says that I have to reinvestigate this. It starts the slow path. It had contacted 2, 3, and 4. This time it contacts only 2 and 3. It's not learning anything new, but now it's able to commit and it's able to say that, yeah, I don't have a dependency on B. What changed?
Okay, so the reason for the slow path is just to notify the other nodes that they need to be dependent. They need to be aware of this dependencies for A. The good thing about 5 was at least F which is equal, which is 2. 2 nodes knew about A. So even if they build a dependency graph on their own, they will have A in their dependencies. However, for 1, it is not possible. 2 and 3 will not know that.
Right. I see. So 1 is not learning anything new, but 1 is teaching something new to 2 and 3, which would be helpful for the recovery pattern.
Yes, it's the slow path is basically to teach the other nodes what is going on before going through a commit path.
Yep. Thank you.
Oh, hello.
Yeah.
Sorry, can I go back? So in the slow path, 1 is actually learning from 2 again, that 2 have learned B about it. Because the first time A contact 2 does not know B. But the second time A contact 2 in the slow path, the 2 now has a B in its dependencies. So that's something new to learn, right?
I see. Yeah. And also from 3 for that matter. Yes.
Yeah.
So actually 1 learns something new. You're right. Yeah. Okay. Interesting. 1 learns that in those actually B comes after it, so it can ignore the case where B comes before it, that it learned from 4, because it learned from 2 and 3 that B comes after A by the power of retrospection, because it retried and it learned about this. Yes, makes a lot of sense.
But I'm not sure if they send dependencies again as a response to the coordinator. Like, for example, in the slow path, the response back, I think, is mostly just an ACK rather than the dependencies again, right?
That's also interesting. Can we check that, or maybe we can check in the discussion?
Sure. Yeah, it's in the pseudocode. Maybe we can check that in the discussion.
Even if it is just an acknowledgement for A depends on B, it is still that something new that true has changed. It's still something that the 1 has to learn that, oh, 2 also agree on this, which is a new knowledge, which does not exist before.
No, actually, this is saying that A would not depend on B. The outcome at 1 is that, nope, I don't depend on B, I will execute first, right?
No, it's actually, there is some dependency on B. It would lead to a cyclic dependency in this particular case, at least.
It would?
Yeah. There is an optimization, which I'll come back, but if you just look at this plain protocol, A has a dependency on B and B has a dependency on A.
Right. This is figure 1 from the paper, right?
No. This is a modified figure. The figure 1 from the paper is I have it as slide 15, which includes the optimization actually.
Let me see. Yeah. This looks like one from the paper. Well,
just like in ePaxes, right? We have the commit that is separated from the execution. So the order of commitment is not necessarily the same as the order of execution in the replicated state machine. So the entire idea here is to learn the dependencies, right? It doesn't mean that slow pass is going to, I'm going to commit and execute right away.
Sure.
No, it's going to commit, but it will have the knowledge of the dependency to know when to execute.
But this is not different than the figure 1 in the paper.
In figure 1 in the paper, basically commit A would have no dependencies. And the part of the reason is basically they prune the dependencies. So if the dependencies were only reported by less than F nodes, they don't include those dependencies at all.
Right, but here, A also does not have any dependency on B. Why would they have dependency on B?
It is just like the non-optimized case where you just, if you just read the pseudocode without going through the example, that is what they do. They just take the union of all the dependencies they have seen so far and then enforce that in the slow path. And this is exactly what this example does. It takes the union of all the dependencies seen in the fast path and then enforces that in the slow path. However, that optimization that they talk about, which is in that figure, basically says rather than taking the union of all the dependencies in the fast quorum, you only take the union of dependencies that are in at least F different replicas that were at least notified by F replicas.
Yeah. Yeah, the slow path coverage in the algorithm was not good. I couldn't follow. I think I didn't learn much from that. But after we talk about fast path and recovery, I thought I understood it. But you are saying this is optimization. In the non-optimized one, both has dependency on each other, sort of. But with the optimization, we can say A does not have dependency on. Yeah, maybe I can. Let's save this for discussion. I'm not able to see it very well.
Sure. Okay. All right. So moving to figure A, the fast path example. So Atlas with F equals 2 can decide fast, but not ePaxos because each of the dependencies are reported, even though dependency A is reported by all the nodes, the other dependencies like B, C, and D are reported differently from different nodes. For example, 2 and 3 have a majority, F majority on B, while 4 and 3 have a majority on D and something like that. So even though different nodes come up with very different kinds of dependency set, Atlas only looks at how many nodes reports each individual dependency. And if it can be sure that at least F nodes can vouch for each individual dependency, then it can take the fast path. This was a gist of the fast path condition. So once you have committed either in the slow path or the fast path, the command goes basically for execution. And differently from ePaxos, Atlas does not have a notion of a sequence number. The reason is basically Atlas only replies to the client after executing the command. While in ePaxos, there was this case where you could reply to the client even before execution. Atlas doesn't do that. And also, because there are no sequence numbers, and also to break ties, similar to ePaxos, Atlas also uses replica identifiers, also proposes that to break ties. If we look at an example on how this execution works, it's largely similar to ePaxos, where there is a dependency graph-like structure, and then you perform a topological sort and break tie cycles with using replica identifiers or any other deterministic scheme, for example. In this example on the figure, I have 3 commands where A is committed without any dependency, but B and C are committed with 2 dependencies each, A, C, and AB respectively. A can go ahead and execute immediately because it does not depend on anyone. But when we draw the graphs for B and C, it will look something like this, where B depends on A, C depends on A, and B and C depend on each other, building a cyclic dependency. And the way we can break this cycle is using deterministic, some form of determinism. For example, you could just use replica identifiers. So if B was having a lesser identifier, then you can just say, okay, B goes first, then C. Otherwise, if let's say you had a small identifier which was smaller than B's, then you can say C goes first, then B. This is the overview of execution. The next one is recovery. Recovery in Atlas is by cases, and the biggest change I saw from ePaxos versus Atlas is that Atlas does round robin style leader change. This, you can compare this with the view stamped replication, where at each view, you know who the leader is. For example, if you are at some ballot, you know, you can figure out who the leader is. And for the other ballot, you can also, using a deterministic scheme, you can figure out who the leader is. So there is no competition for the same ballot, like in traditional Paxos. This is more like view stamped replication. And the recovery at a very high level has two cases. The first case is basically whenever a node steps in and wants to recover some command, it tries to send a message and see what other nodes think about that command, the recovering command. In the first case, if some node already knows that the command has been committed, basically it will send to whoever is requesting that information, that message, and it can, that the requester can be satisfied that way. However, if the requester doesn't receive any commit responses because it has not been committed, then it would expect information from about n minus f nodes, which is the phase 1 quorum of flexible Paxos. From this information, it would take two decisions, basically, at the very high level. So one decision is if some node reports that there has been a slow path taken for that command, then the recovery phase basically repeats the slow path and commits that command. The tricky case is basically when the slow path is not observed by any node. So if the slow path was not observed by any of this n minus f nodes, we need, there are at least 3 subcases to consider. The first subcase is if in that reply the requester gets, if one of the reply is from the initial coordinator. Initial coordinator is the one who started the proposal for that command initially. In some cases, the coordinator may not have been able to even reach a fast quorum, for example, or like even get any reply from the nodes because of some network partition or something, but it is able to assist in recovery. So if the initial coordinator replies, then the condition is that the fast path was surely not taken, because otherwise the initial coordinator can simply send a commit message and be done. So if the coordinator replies, it means the fast path was surely not taken. So which means the node that is trying to recover the command, the new coordinator, can simply repeat the slow path by taking a quorum of any quorum of reply. This is important because the coordinator did not make any decision, so the recovering replica is able to take any quorum to enforce its decision, basically. Differently, if the initial coordinator does not reply, then it is possible that the fast path was taken or was not taken. And in this case, it is very important for Atlas to include the nodes from the original quorum. Otherwise, it will not know anything about the decision that was taken by the original leader. In ePaxos and other protocols kind of relax this, and they deal with some slow quorum, which is already a majority. However, because the quorums are small in Atlas, they have to specifically get those exact replicas. They have to specifically target those exact replicas, which may have information about the command they are recovering. And they do a slow path with the dependencies that they specifically get from those nodes, in addition to the replies that they got while collecting the information during recovery. Also, there is the third condition when no process observes the initial quorum because some node did not have any information on that command or of some sort, basically. In that case, propose a no op in the slow path and propose that new command in a different proposal as a fresh command, basically. So this is the gist of recovery. There are some more subtleties that I may have missed, but overall, I think this captures it. Moving on to the two optimizations that the paper does. The first optimization is bringing back our first example where I spoke about the normal case. In this example, as Murat pointed out, basically the slow path commits command A with B as the dependency. However, the example in the paper basically says that A can commit without any dependency. The way they do it is having the slow path optimization. So rather than including all the dependencies that they received from the fast quorum and enforcing them in the slow path, they just enforce those dependencies that have at least that are at least reported by F nodes. So in this case, B was reported by only one node, while other nodes report an empty dependency, right? So in the optimization that Atlas does is prune dependencies that are collected from less than F nodes, and which yields us a smaller dependency set. In this case, the dependency set is empty because we removed B because it was only from one reported by one process. So this optimization is all Atlas uses throughout their evaluation, and even the figure represents that, because they believe reduces the dependency, the execution algorithm, basically the overhead of the execution. The second optimization they do is called non-fault tolerant reads. Their observation for this is basically that some later commands need not depend on reads. So for example, in this case, we have three commands, let's say W2, R, and W1. W2 and W1 are writes, while R is a read. So R depends on W1, W2 depends on R as well as W1 in a graph, basically. The point here is that W2 does not even need to depend on R. It only has to depend on W1 because we know that R does not make any change to the state, right? So in that case, whenever you enforce, whenever you do reads, let me rephrase it. So basically, whenever a write depends on a read, you can make those writes not depend on those reads, especially when those reads are non-fault tolerant. So what they mean by non-fault tolerant is you can propose a read command that executes as soon as a majority of replicas send an ACK for that command, basically. So they call this non-fault tolerant read. And what that allows them is basically reads can never block, such reads, especially non-fault tolerant reads, can never block any write. So for example, even if R was lost, nobody has to even recover R, because the only reason you would recover it is basically because it was dependent on some, it is blocking some write in the usual case, right? In this particular case, you don't even have to recover R. If it is lost, you can just leave it as it is and just issue a new read request. And your writes would never be blocked. And this optimization they basically use for the YCSB benchmark in the evaluation. Moving on to evaluation, they evaluated three protocols: Atlas, ePaxos, and Flexible Paxos. by deploying on in different sites from 3 replica configuration all the way to 13 replica configuration in increments of 2, basically. And at each site, they have 1 replica, similar to what ePaxos did. And for Atlas, they visited 3 different values of F, 1, 2, and 3. And they did a bunch of experiments. The first one was basically, they showed how many fast paths can Atlas really get at different F values. And because of how Atlas works, if you set F equals 1, you will always get a fast path, because if the node that proposes a command reports some dependency, that is more than enough. No other node has to report any dependencies. And that is trivial. So Atlas is able to go fast whenever you set F equals 1 at all. And it is oblivious to contention, basically. However, like as you said, if you increase F to 2 and 3, you can really start to feel the effect of the dependency graph and then dependency exchange and validation. At F equals 3, basically Atlas almost comes as close to ePaxos with F equals 2. And basically the reason is more conflict means more slow paths for even Atlas, even though F equals, even though F is a very small value. Moving on to the latency graph, I put these 2 figures side by side because they both deliver the same result, except they slightly modified the experiment. One on the left is 1% conflict rate, while on the right it's a 2% conflict rate with different number of clients. However, the performance difference felt almost similar when I looked at it. One thing we can look in figure 5, they have this black bar where this is the optimal latency for any protocol if they simply do a fast path. So this latency includes the client communicating to one closest node and that node doing an optimistic fast path. It does not care about any dependencies or anything. It's just it is like fast Paxos without any contention. So that is what optimal does, basically. And what they're able to show is Atlas is able to meet that optimal latency depending on the number of failures, especially at node 5. If you look, Atlas and ePaxos have the same quorum because and because of that, they don't have any difference in their latencies. They both perform the same. This is the same quorum I showed in the example when I was building the Intuition for ePaxos and Atlas quorums. But as the number of nodes increases, the latency difference between ePaxos and Atlas increases because Atlas reaches fewer nodes while ePaxos reaches many more nodes. For latency versus throughput, the throughput provided by both Atlas and ePaxos are all the same. The only big difference here is between their latencies. And again, it's because the number of faults that Atlas is able to tolerate versus its quorum size. The interesting part was the YCSB benchmark, especially because they use this NFR optimization. I'm just showing here a workload, a configuration with only 7 sites. There is another 13-site configuration in the paper, which has similar results. In this configuration, you can see that whenever the NFR optimization only works if you have reads and writes at the same in the system. Like if you have 100% writes, the optimization simply don't give you a lot of benefit. Although I couldn't understand why it didn't give any benefit for Atlas F equals 2, because according to the text I read, the reads do not conflict with reads. So I don't understand why they only say Atlas latency is about 1x, whereas for Atlas F equals to 1, it does 1.3x in a read heavy workload. But otherwise, whenever you have equal writes and reads, the impact of NFR optimization basically lets any writes execute faster without depending on the commit order for the reads, for example. And I think that's all my slides are.
Cool. Thank you so much. This was excellent presentation, and we can now move on to the discussion.